The synthoscope, a vision for combining synthesis with atomic fabrication. This manuscript was published in the journal Advanced Materials in 2023. The scanning transmission electron microscope is a workhorse instrument for materials characterization. Recent work has begun to utilize this instrument not only for characterization, but also atomic manipulation. In this manuscript, we lay out a vision for the future development of this instrument toward an expanded set of capabilities and applications. Specifically, we propose that the incorporation of in situ synthesis techniques will complement and amplify current atomic fabrication capabilities to facilitate the development of atomic scale manufacturing. We begin by introducing the concept of a chamberless synthesis environment, or CSE. Typically, synthesis is performed in some kind of reaction chamber, where we have control over various aspects of the environment. We can adjust the temperature, the partial pressure of various gases we flow into the chamber. There are many ways we can influence the materials within the chamber to drive a synthesis process and obtain a new material. In the stem, we pass a highly focused electron beam through our material, which creates a highly localized disturbance. This frequently causes materials to transform in one way or another under the beam. We can think of this local disturbance as a synthesis chamber the size of an atom. Since it is not really a chamber, we can call it a chamberless synthesis environment, or CSE. We already have examples of synthesis in a CSE. Electron beam-induced deposition, or EBID, is a technique where a precursor gas is flowed across a substrate. The electron beam is used to dissociate the precursor into chemically reactive fragments. These fragments then spontaneously bond to the substrate, leaving a deposit. We can describe this process as a synthesis reaction in a CSE generated by the interaction volume of the electron beam and the materials. EBID is typically performed in an SEM, but Van Dorp et al. Performed a series of studies aimed at doing EBID in a STEM and pushing it to the limit of resolution. Ultimately, they were able to show that they could deposit material molecule by molecule on a graphene surface. From the EBID perspective, molecule by molecule deposition is as precise as the technique can get. The precursor gas is composed of molecules, and therefore the smallest unit one can deposit is a molecule, or molecular fragment. It cannot quite get down to single atoms. The EBID perspective has boxed us in by prescribing the chemical reaction we expect to observe. However, the CSE perspective is agnostic to what should happen. It merely asserts that some reaction could happen. If we abandon the idea that we must dissociate a precursor gas, we can instead simply consider what would be required to drive a reaction in the CSE that would result in the deposition of a single atom. In fact, we already have examples of single atom deposition. Here, the electron beam was used to damage specific locations of a twisted bilayer graphene sheet. At the same time, the sample and nearby copper nanoparticles were held at around 1,000 degrees Celsius, which promoted the evaporation and diffusion of copper atoms to the damaged locations, where they could chemically bond to the surface. Here's a conceptual animation. The electron beam first ejects an atom from the substrate. This makes the substrate chemically reactive. When a diffusing add atom comes along, it can bond to the defect site. The example with copper atoms conceptually looked like this. We have copper nanoparticles sitting on the surface with everything held at high temperature to promote the evaporation of the nanoparticles and the diffusion of atoms across the graphene surface. However, ideally, we would like to put the source material elsewhere to maintain the cleanliness of our graphene. We would like the conceptual situation to look more like this, but we need a way to supply atoms to the surface. Now, this situation is starting to look like a special case of synthesis. We are manipulating environmental parameters to facilitate some desired chemical reaction or material transformation on a substrate. But the reaction does not take place until we manifest the CSE by E-beam irradiation. So how can we supply source atoms to a sample without redesigning the whole microscope? We present two possibilities that represent concrete examples of a simple way this could be done with existing hardware. In the first example, we start with the commercially available neon electrical cartridge. A custom-designed insert is envisioned that consists primarily of a printed circuit board attached to a base plate that will slide into the cartridge. At the end of the PCB are contact pads to which an evaporative filament is attached. The filament would be able to operate in situ, and any material that was put on the filament could then be evaporatively delivered to the sample. An alternative strategy could be to use in situ pulsed laser deposition. Here, the laser could enter the microscope through a viewport and be focused onto a target to evaporate it. In our concept drawing, we furnish 3 different targets, which would enable the user to switch elements on the fly. Using simple strategies such as these, we believe that atomic scale synthesis processes could become a matter of routine. Coupled with automated beam control and AI-driven analysis and discovery, the synthoscope concept offers a unique approach toward atomic scale manufacturing and a window into atomic synthesis processes generally. Links to the publication may be found in the comment section below.